Welcome to The Explainer. We're going to dive into a pretty wild idea today, one that could totally shake up our understanding of physics. And it all boils down to a really simple question about what we think of as empty space. So what if the vacuum, that supposedly total nothingness between all the particles, what if it's not nothing? What if it's actually a physical substance with its own rules and properties? Now, I know it sounds a little like sci-fi, but hang on, because this one idea might just be the key to solving some of physics' most stubborn mysteries. All right, to get why anyone would even propose such a strange idea, we have to start with something that's already known, a bizarre but totally proven fact about the very forces that hold our universe together. Here it is, and it's a real mind-bender. The so-called constants of nature, like, say, the strength of an electric charge, they're not actually constant. Nope, their strength actually changes depending on how you look at them, specifically at what energy you're probing them. And this isn't just a theory. This is something we've seen in experiments for decades. It's real. And here's where it gets even weirder. Different forces change in opposite ways. For instance, if you get really, really close to an electron, probing at high energy, its electromagnetic force actually appears to get stronger. But if you do the same thing with a quark, the strong nuclear force that glues it to other quarks gets weaker. That last part, by the way, was a Nobel Prize-winning discovery called asymptotic freedom. So, what gives, right? If these things are supposed to be fundamental laws written into the fabric of the universe, why on earth do they change depending on our point of view? What is physically happening out there in the vacuum to make this happen? Okay, so how does mainstream physics explain this? Well, the standard model is incredibly good at what it does, but it comes with this, let's call it a major conceptual headache. A really big one, actually. The problem of infinity. The official explanation is this powerful mathematical toolkit called the renormalization group. And look, it's brilliant. It gives physicists the tools to calculate exactly how these forces change with energy, and its predictions are ridiculously accurate. We're talking some of the most precise predictions in the history of science. But, and this is a huge but, while the math works beautifully, it's really hard to say what it all means in the real world. You see, to get those amazing answers, the theory has to perform some pretty tricky maneuvers to tame calculations that, on their own, just want to blow up to infinity. To stop everything from blowing up, physicists have to stick something called a regulator into their equations. You can think of it like a mathematical patch, an arbitrary cutoff they have to impose just to get sensible, finite numbers out at the end. And that leads us to the real, nagging question that sits at the heart of all this. What is that regulator in the real world? Is it just a mathematical trick we have to live with, or is it a signpost pointing to some deeper physics that our theories are just completely missing? The standard model? Well, it doesn't have an answer. So, if the standard picture leaves us with this big, gaping conceptual hole, is there another way to think about all this? Yes, there is. And it's a radical new take called dynamic vacuum field theory, or DVFT for short. And here's the fundamental shift in thinking. On the left, you've got the old idea. The vacuum is just an empty, passive stage where all the physics happens. But on the right, the new idea from DVFT, nope. The vacuum isn't the stage, it's one of the actors. It's a physical player that's part of the action. This new theory proposes that what we call empty space is actually a real physical medium. Just like water or air, it has properties. It can have a density, it can have a structure, it can even have a stiffness. DVFT gets pretty specific about these properties too. It says the vacuum has an amplitude, which is basically its density. It has a phase, which you can think of as its internal structure or organization. And most importantly, it has stiffness, which is a measure of how much it resists being disturbed. So why is this so powerful? Because this one idea, that the vacuum is a real physical medium, suddenly makes all those mysteries we were talking about seem incredibly simple and intuitive. Okay, let's walk through this because the logic is just beautiful. First, in this picture, a force is really just a measure of the vacuum's stiffness. Simple enough. Second, this vacuum medium isn't perfectly smooth. It's got tiny fluctuations at every scale, like little ripples on a pond. Third, when you probe it with really high energy, you're essentially zooming in and averaging over a much smaller patch, with fewer of those ripples. And that means, fourth, the average stiffness you measure changes. So of course the strength of forces changes with scale. It's not a mystery, it's a basic property of any physical medium. So all of a sudden, that super complicated physics term, running coupling, becomes something you can actually visualize.
It's just the changing elasticity of space itself. The big mystery just dissolves.
But what about the infinities in that mathematical regulator? Well, this is the real killer app of the theory. DVFT says that regulator isn't just a trick, it's a real thing. It's a physical cutoff. The idea is that the vacuum itself has a kind of graininess, a sort of atomic scale where it stops being a smooth, elastic thing. And that scale is set by real, massive particles that make up the vacuum itself.
So if this theory is right, what does it mean for physics? Well, it suggests that the infinities that have been haunting our best theories for a century, they might not be real at all.
This is the huge payoff. Where the old physics runs into a brick wall of infinity, DVFT sees a warning sign that just says, hey, your theory is being pushed too far. For example, there's a famous problem called the Landau pole, where the math says electromagnetism should become infinitely strong at tiny distances. DVFT says, no way. That's just the point where the vacuum stops behaving like a simple elastic sheet and its true, more complicated nature takes over. No infinity required. The big takeaway here is pretty profound. Infinities were never a feature of the universe. They were a bug in our theories. A bug caused by one simple, wrong assumption, that the vacuum was empty and featureless. Give the vacuum its physical properties back, and the problem of infinity just goes away.
And that leaves us with this incredible final thought. If the one thing we all thought was the absolute simplest thing imaginable, empty space, is actually a complex, dynamic physical medium, well, it just makes you wonder, doesn't it? What other fundamental secrets about reality are hiding in plain sight, just waiting for us to look at them in a completely new way?